babe? Want to play a game?
Sure.
So the game is, we have two piles of stones, one with 10 and one with 15. Now we alternate turns, and whoever's turn it is takes as many as they want from one, or as many as they want from the other, or you can take the same number from both. So I could take 2 from each, or I could take 6 from here, or I could take 13 from here. And whoever takes the last stone is the winner. Does that make sense?
Can I take different numbers from both?
No, for example, you can't take 3 from here and 4 from here. You have to take 3 and 3.
Okay, that makes sense. I think you should start.
I'll go first. I'll take 2 from each.
Okay, I think I will take 4 from here.
Okay. I'll take 6 from here. 1, 2, 3, 4, 5, 6.
I think I will take another 4 from here.
I'll take 2 from each.
I'm gonna take these 2.
And I'll take the last one.
Oh, so you win.
I do.
Okay.
So I won. How did I do it? That's what this video is going to be about. This game is called Wythoff's NIM, and we're going to derive a complete winning strategy for it that you can compute in your head. Along the way, we're going to need 3 tools: combinatorial game theory, Beatty sequences, and the Zeckendorf representation of a natural number. The first half of the video will be us explaining each of these tools, all of them starting with a seemingly unrelated question to introduce the topic. Then we're going to begin dissecting Wythoff's game and weave these tools into an eternal golden braid that produces a solution. So come along and enjoy the tapestry we create. Want to play another game?
Sure.
All right. So the game is, you start, you say a number, and I subtract 1, 2, 3, or 4 from that number. And then you subtract 1, 2, 3, or 4 from my number, and we alternate back and forth. And whoever says 0 is the winner.
Okay.
Make sense?
Sure. But what are the stones for?
Nothing. All right, ready to go?
Sure.
You start.
37.
35.
31.
30.
28.
25.
24.
20.
16.
15.
12.
10.
8.
5.
1.
0.
Oh. You won again.
Good game.
Good game.
That's true. This is an example of a good game. It's called a combinatorial game because there's no chance involved anywhere. There's no die rolling, there's no card shuffling, there's no coin flipping anywhere in this game. It also has no hidden information. Everyone can see exactly what state the game is at any given time. I kind of want to say it's a fair game because no one can cheat because everyone can see what state the board is at any given time, but that's not what fair means, so never mind. In any case, my lovely wife identified, but didn't get a chance to take advantage of, one of the key components of analyzing any combinatorial game: separating the states where I have an advantage from the states where I don't. We'll visualize the game states as these blocks, with arrows representing possible moves. Let's get a few more states in view. In this game, the states where I had an advantage are the red ones, those that ended in 0 and 5, and the ones where I didn't are the green ones. What does it mean that I had an advantage? Let's dig into it. We say a position is a winning position if, when it's my move, I have an advantage. If I played my best, whatever the other person does, I can win. A losing position, conversely, is one where no matter what I do, if the other person knows what they're doing, they will win. If the game has ties, there are tying positions, where if both people play perfectly, the game is a tie. So in the game we just played, the losing positions are the numbers ending in 0 and 5, and the winning positions are everything else, there being no tying positions. As a hint, notice that from every green box, there's a move to a red box, and from every red box, there's only moves to green boxes, because I could always get to a multiple of 5 from any number she said, and she couldn't ever get to one from what I said. Obviously, the most important question when analyzing any combinatorial game is to determine the winning positions and losing positions. You win if you're given winning positions, and you hand your opponent losing positions, by definition.
Sounds simple, but this small observation gives us an immense power. We can recursively decide if a position is winning or losing, just based on where you can move to. If you find yourself in a winning position, to win, you need to find some way to give your opponent a losing position. If you can't, then you weren't ever in a winning position to start. So a position is winning if there is at least one move to a position that is losing. And if you find yourself in a losing position, you can't help but move to a winning position. If there were some move you could make to a losing or even tying position, you wouldn't have been losing. So we learned that a losing position is one where every move takes you to a winning position. And for completion's sake, if you find yourself in a tying position, what is true? You need to be able to move to another tying position, but you can't move to a losing position, since that would mean you started at a winning position. So a position is tying if every move either leads to another tying position or a winning position, where there is at least one of the former. Well, great. We've defined winning, losing, and tying positions in terms of winning, losing, and tying positions. Whoop-de-doo. Love circular reasoning. Well, it's circular reasoning in the same way that induction is circular reasoning. Remember when I said recursively, there are certain positions that you don't need to step backward anymore to say whether they're winning or losing. These are the ending states. In the game we just played, if you receive the number 0, you have already lost, so you are losing. And 0 is a losing position. That's your base upon which to build the recursion. The state 1 can move to 0, so 1 is winning, as are 2, 3, and 4. And then 5 can only move to 1, 2, 3, and 4, which are all winning, so 5 is losing. And we build up and up all the way through the integers and find out what we knew from the beginning. The numbers ending in 0 and 5 are all losing, and everything else is winning. So to analyze a game, we first find all ending positions and determine if they are winning or losing. Then since winning only means some move to a losing, look at everything that can move to the losing final positions and label them as winning. Then look at the smallest undecided position, smallest meaning all its next possible states are decided. It must be losing, because anything that could be winning was discovered already. Everything that had a move to a losing position has been accounted for. Then we repeat. Everything that can jump to that losing state is winning, and we find again the smallest undetermined state, which must be losing. In the end, we're able to cover every single state, because if there were some point where we couldn't step back anymore, then at that point, every undefined state would need to have some move to some other undefined state. But then repeatedly choosing one and following it gives us an infinite game, which is impossible in a well-ordered game, whatever that means. So eventually, we've hit every state and know whether it's winning, losing, or tying. But knowing this information for every state is enough to always win, and so we call the game solved.
This backward searching technique could theoretically be applied to any combinatorial game like I discussed at the beginning, those that have no hidden information and no reliance on any chance. That includes games like tic-tac-toe, Connect 4, checkers, and chess, assuming that we've beefed up the techniques so that it includes ties as well as winning and losing. But notice I said theoretically, because the technique involves looking at every single possible state that it could ever exist. For tic-tac-toe, that's easy because there's only 9 factorial ways to line up the squares in the order in which they're played, so there's at most 9 factorial states, and a computer can handle that many easily. But for Connect 4 and higher, the number of states is way too high for a computer to have any chance of analyzing it. So the technique moves from considering every possible state to considering only responses to moves that opponents could possibly make, and doing it at runtime instead of pre-computing it beforehand.
So to introduce Beatty sequences, we're going to start with a basic question. Given any natural number of digits, what is the largest power of 2 and largest power of 5 that have that many digits? So for 1 digit, it's 2 to the 3, which equals 8. For 2 digits, it's 2 to the 6, 64. For 3 digits, it's 2 to the 9, 5, 12. And then for 4 digits, it's 2 to the 13th. For 5, it's 16, then 19, then 23, 26, 29, and 33. For powers of 5, with 1 digit, it's 5 to the 1. For 2 digits, it's 5 to the 2. For 3 digits, it's 5 to the 4, then 5 to the 5, then 5 to the 7, 8, 10, 11, 12, 14. So what kind of question is this? I mean, it's just a list of random exponents. Well, let's actually check which exponents occur. So we have a 1, a 2, we skip the 3, but the 3's over here. Then 4, 5, we skip the 6, but the 6 is over here. 7, 8, 9, 10, 11, 12, 13, 14, and the pattern continues. The next one is 5 to the 15th, and then 2 to the 16th, etc. Well, that's interesting. It looks like every exponent occurs on one side or the other, but never both. And so that's what we conjecture, is that every exponent occurs on one side or the other. And this is actually a theorem of Rayleigh about Beatty sequences, and we're going to prove that in this section. Now, to prove this, we'll look at how to actually find the right answer for any number of digits without guess and check. We know that the largest number with n digits is 10 to the n minus 1. So we're looking for the largest m, where 2 to the m is less than 10 to the n. Take log base 2 of both sides, and we get m is less than log base 2 of 10 to the n, or m is less than n times log base 2 of 10. So then, since we're looking for the greatest integer less than n times log base 2 of 10, we learn that m must equal the floor of this. And similarly, the sequence of exponents with the 5s is n times log base 5 of 10. So it appears that these two sequences cover every natural number exactly once, as n ranges over all natural numbers. Here we see that 3, 6, 9, 13, and so on are covered by the first sequence, and 1, 2, 4, 5, 7, and so on are covered by the second sequence. Beatty sequences are generalizations of these, where log base 2 of 10 and log base 5 of 10 are replaced with alpha and beta greater than 1. Clearly, there needs to be some relationship between alpha and beta. What is it? Well, some heuristics should help. Thinking about on a long range, approximately what fraction of integers are covered by alpha times n? It would be about 1 alphath. And how many by beta? Again, 1 betath. In order for the whole line to be covered without overlaps, the total fraction should be exactly 1. So 1 over alpha plus 1 over beta is equal to 1. Is this true with our alpha and beta? Yes, by change of base formula for logs. See the demonstration here. So our claim is that if alpha and beta satisfy this, then the floor of the arithmetic progressions with differences alpha and beta cover every positive integer. Great! Let's try alpha equals beta equals 2. So the ANs are equal to 2, 4, 6, all the even numbers. And the BNs are equal to the same thing? Whoops, that went wrong quickly. Maybe alpha equals 3 and beta equals 3 halves? Again, the ANs equal 3, 6, 9, and the BNs equal 1, 3, 4, 6, and so on. So no, they both hit 3. What's the problem? The problem is that if alpha and beta are rational, they will eventually both hit the LCM of their numerators, and they therefore can't partition the integers 1 to 1, since they'll both hit the same number. So we'll assume that they're irrational. Now this is a true theorem, and we're going to investigate it. What does it mean that m is equal to the floor of alpha times n? It means that m is less than or equal to alpha times n is less than m plus 1, or strictly less than, since alpha is irrational and n is positive. But therefore, m over alpha is less than n is less than m over alpha plus 1 over alpha. Rearranging to put m in the middle, we get m over alpha is between n minus 1 over alpha and n. So n would need to be the ceiling of m over alpha, but only if m over alpha is within 1 over alpha below an integer. And then what about beta? It's the same. But here's the key. M over alpha and m over beta add up to an integer, right? Since 1 over alpha plus 1 over beta equals 1, m over alpha plus m over beta equals m. So let's draw two number lines, one for n and one for k. We need the integers, these vertical bars. And we said that m over alpha and m over beta add up to an integer, so without thinking too hard, we'll start them both at integers. Then we look at the segments where m appears in the two sequences. They are these green segments directly below all the integers. The ones on the top line have width 1 over alpha, and the ones on the bottom line have width 1 over beta. Then the red segments represent where m doesn't appear in the sequence. Notice that the red segments are the same length up top as the green segments are below, and vice versa, because 1 over alpha plus 1 over beta equals 1. Now we begin moving the lines around, where the top shifts left the same amount the bottom shifts right. Notice that no matter how we shift it, either the top one or the bottom one is in the green and the other is in the red, because the lengths of the segments are exactly complementary. So as a recap, whatever m is, either m over alpha lands in its green region, in which case m can be written as the floor of n times alpha, or m over beta lands in its green region, in which case m can be written as the floor of k times beta. Only one of these can happen, and exactly one of these must happen. And that's why this theorem of Rayleigh about Beatty sequences is true.
So another proof, which is a little bit more hands-on, involves rewriting what it means to actually be in one of the two columns in a different way. So we have a bunch of equivalences here. N appears in the 2 to the k sequence if and only if 2 to the n starts with 5 through 9. N doesn't appear in the 2 to the k sequence if and only if 2 to the n starts with 1 through 4. N appears in the 5 to the k sequence if and only if 5 to the n starts with 2 through 9. And doesn't appear in the 5 to the k sequence if and only if 5 to the n starts with 1. Now these shouldn't be very difficult to figure out why they're true. For example, this one, 2 to the n starts with 5 through 9. That is only necessary so that when you multiply by 2, it carries and rolls over to the next number of digits. And similarly down here, if you have a power of 5 that starts with 2 through 9, you multiply by 5, it's going to roll over and carry into the next number of digits. And that's not true if it starts with 1. So now, if that's true, what we're going to do is we're going to take these and rewrite them in terms of inequalities. So 2 to the n starts with 5 through 9, if and only if you can trap 2 to the n between 5 times the power of 10 and the next power of 10. And similarly, it starts with 1 through 4 if you can trap it between a power of 10 and 5 times that power of 10. And similarly down here. So what we're going to do is what we need to be true is we need these two to never happen at the same time, and we need these two to never happen at the same time. Right? We want either it to occur in one of the two columns or in the other of the two columns. We can't have them in both, and we can't have it in neither. So what that means is we want the 2 star inequalities to never be true, and we want the 2 double star inequalities to never be true at the same time. But look what happens if we take the 2 star equalities and multiply them. We get 10 to some power is less than 10 to the n is less than 10 to the next power. So we've trapped 10 to the n between 2 consecutive powers of 10, where equality can't happen, so that's impossible. And similarly, for the 2 double stars, if you take them and multiply them, you get 10 to some power is less than 10 to the n is less than 10 times the next, or 10 to the next power, which again, you've trapped 10 to the n between 2 consecutive powers of 10. So those can't happen, and so it's impossible for the 2 1 stars, and it's impossible for the 2 2 stars to occur at the same time, which is exactly what we wanted, and that's the proof.
Your challenge is to convince yourself that this is the same proof as the one from before, and see how to extend it to every pair of alpha and beta. Also, there was some difficulty with the endpoints. Where does that manifest itself here? And what is the corresponding trouble if alpha and beta are actually rational? Finally, here's a different way to write it. Your challenge is to prove that this formulation, replacing floor of beta times n with ceiling of beta times n minus 1, ceiling being the smallest integer greater than, rather than the largest integer smaller than, that this formulation is true even for rational numbers, and the two sequences partition every integer, positive, negative, and 0, as n runs over all integers. Try first to see how it fixes the problem with alpha and beta both being 2.
Let's play another game. I have a couple bins here and a bunch of stones in this bin. This bin is a black hole because it's the end of the table, so any stone that goes into it disappears. And this bin has a portal to this bin, so that any stone that lands in here actually lands in here, so we can just ignore that for the rest of the game. Otherwise, the rules of the game are, if you have 2 stones in the same bin, you can take them out and move one up, move the other down 2. Or if you have 2 in consecutive, you can hop one over the other and take the other one away. So the question is, if you continue to do these rules, will it always end, and will it always end in the same position? It ends, of course, when you can't do either of these moves, when there's no stones that are in consecutive bins, and when there's no stones in the same bin. So the rules for the end here are a little bit more complicated. If we take 2 and we were to split them apart, this one goes into the black hole, this one moves up. So really what happens is we can take 2, move one up, and throw the other one away. And then this one, if we take the 2 and split them, one of them goes here and one of them goes into the portal, so it really goes back here. So what happens is, if we have 2, we can split them up, move one here, and move one here. Otherwise, the rules are as I stated, and again, the questions are, if we play this until the game ends, will we always be able to stop? And will it always stop in the same place? Let's try it with 100 here. I'll conspicuously split 38 pairs and leave 24 behind. So now there's 38 and 24. Next, I'll jump all 24 over these, leaving 14 behind. Then I'll do the same thing. Jump all 14 of these, leaving 10 behind. Then I'll jump 9 of them, leaving 1 behind. Then I'll jump all 5 here. Then I'll leave another one behind and hop the remaining 3. Then we hop these last 2, the last one, and this last one. And we end with 1 in the 3rd bin, 1 in the 5th bin, and 1 in the 10th bin. Let's try it with a more realistic sequence of moves. So we end at the same place. Amazing! Before going any further, we'll study the rules just a bit. Notice that if we have 4 bins in a row, leaping this pair lands us with 2 in the same bin, but leaping this pair lands us in the spread configuration it's equivalent to. So needing to do the spread configuration is just the universe telling you that, you screwed up, should have done this jump first. And however we plan to analyze the jumps, we can really just study the leapfrog move, because the spread move is a combination of 2 of these, one in reverse and the other being forward. As an aside, you may have noticed that in the first method, other than the first step of splitting, which we can't avoid, we skipped every single splitting step, and decreased the number of stones by 1 every turn, whereas in the longer method, we did make some of these wrong jumps, and doing the accounting and adjusting for these splitting errors, we actually make the same non-erroneous steps as in the first one. Let me run through the sequences one more time, and I'll post some strange numbers above each bin. At each step, we multiply the number for each bin by the number of stones in it. Notice that no matter where we are, the answer is always 100. What are these numbers? And what property do they have? They're called the Fibonacci numbers, like no matter how many we start with in the first jar, 8 and 13 and 21 will always be Fibonacci numbers. And just like the leaping move, the sum of any 2 consecutive is equal to the next. In fact, that's why the sum property is preserved. We replace 2 stones worth 2 Fibonacci numbers with the stone worth their sum. And notice that the black hole bin is worth 0 and the next 2 bins are both worth 1, so the disappearing and portal rules are satisfied too. So what about this game? What do we want to show? Our goal is to show that first of all, it actually ends and can't go on forever. Second, we want to show that it always ends in the same state, no matter what sequence of moves you make. Once we show these 2 things, we'll analyze what it says about the Fibonacci numbers at the end of the section.
So why does the game need to end? We can actually order the states. If we take two positions, we look from the right, and the first bin to the right, where the two positions differ, whichever has more in that bin, we say that state is greater. This is a coherent comparison, it's transitive, it makes sense, and it gives us a way to order all possible states we could land ourselves in. Also notice that when we do either of the moves we can, comparing before and after, the new state is always greater than the old state. So we're always increasing the state, there's only a finite number of possible states you could be in, and so there's no cycling and we must always end. However, that only shows that it will always end, not that it will end at the same place. So why might that be? I'm claiming that if the number of stones you start with is between two Fibonacci numbers, there's no ending state that does not include that Fibonacci number. Why?
Well, we'll first rearrange it to prove the converse.
And then we can say that n can only be in one such interval, and the top ball can only be in one jar, so they're one-to-one matching with each other, and the original statement must be true too. The first half of the inequality is obvious, since the starting position and ending position both have value n, so we work to prove the other side. So we start with any ending state, remember meaning that no two consecutive bins have a stone and no two stones are in the same bin. At every step, we increase the value of this state by taking the rightmost stone and moving it as far right as we can. So we start with this state here, with Fibonacci value equal to n, and we move this stone right, then this stone can be moved to here, then over here, and wherever there's an empty bin in a usable spot, we put a ball there, at every step increasing the Fibonacci value. Eventually we end here, with the 2, 5, 13, etc. bins with a stone in them. If we add just one more stone in the one bin, we can hop our way to a single stone in the next bin, ending with a final value of fk plus 1. And so we showed that n plus 1 is at most fk plus 1, meaning that n is less than fk plus 1, which is what we wanted. And that's what happens if k is odd. If k is even, the setup shifts 1 to the left, and adding the 1 puts 2 in the first bin, and then the same jumps do the same thing to prove that this value is equal to fk plus 1, and so again, n is less than fk plus 1 as required. So as a recap, here's what we did. We took any ending position that was completely less than this bin, increased its value by some amount, and then added 1 and ended alone in that bin. So that shows that every such ending position must have starting value less than fk plus 1. So the ending position with a value between two Fibonacci numbers must include that bin, and we're therefore sure of the largest bin a stone must end in. So we can remove that stone and in parallel the stone's value, and we're again sure of the next bin a stone lands in, and we just build up the ending position as it must be. As an example, we can look at 100. It is between 89 and 144, so it must include an 89, and what's left over equals 11. Then 11 is between 8 and 13, so it must include an 8, leaving 3 left over, which can be placed in the 3 bin with nothing left over. So after playing this game, we've incidentally learned that 100 can be written as 3 plus 8 plus 89, which is the 4th Fibonacci number plus the 6th plus the 11th.
And the generalization is obvious. There's always exactly one way to write any non-negative whole number as the sum of unique, non-consecutive Fibonacci numbers.
So what have we done? We've shown a game you can play, a procedure, and we showed that no matter how you play the game, if you start with the same number, you will always end at the same state. And then attaching Fibonacci numbers to that end state, we showed that there is always a unique way, given any integer n, to write it as the sum of distinct non-consecutive Fibonacci numbers. That representation is called the Zeckendorf representation.
We need one more fact about Fibonacci numbers, namely their closed form. This is called Binet's formula, and it's written here. If you don't want to see my derivation of it, skip to 3538, but otherwise, here we go. There will be 5 steps to this proof. We generalize the Fibonacci sequence by removing the starting requirements, but keeping the recurrence relation, and write down another important sequence, the Lucas numbers. Then, we prove that every such sequence is just a combination of the Lucas and Fibonacci numbers. We next introduce a transformation of any such sequence into another one, and figure out how it acts on the Fibonacci and Lucas sequences. Finally, we take a Fibonacci-like sequence that we can write down an exact form for, and use the transformation to figure out its Lucas and Fibonacci parts. Trust me, it'll be worth it. we first introduced the idea of Fibonacci-like sequences. They are sequences of numbers, infinite in both directions, that satisfy the recurrence, but not necessarily the same starting point as Fibonacci. For example, we can introduce the Lucas numbers, L0 equals 2 and L1 equals 1, and the sequence continues 3, 4, 7, etc. And we can extend it and the true Fibonacci sequence backwards. If these two must add to this, then this minus this should equal this. So the Lucas numbers extend backwards as -1, 3, -4, 7, etc. And Fibonacci starts 0, 1, 1, 2, 3, and so on, and extends backwards 1, -1, 2, -3, and so on. The first thing we do is show that there aren't really very many such sequences. In fact, if we take any sequence with its given a0 and a1, we construct the sequence Bn given by a0 over 2 times the Lucas number Ln plus a1 minus a0 over 2 times the Fibonacci number Fn. Notice that b0 collapses down to a0, and b1 is a bit more involved, but it too collapses down to a1. And finally, plugging in for bn plus 1, the autopilot proves that the B sequence inherits the relation from Lucas and Fibonacci. So the B sequence equals the A sequence for 2, for 3, for 4, and forever to infinity, and of course we can reverse the process and learn that the whole sequence is the same as the A's, even into the negative integers. So the original A sequence is just a linear combination of the Lucas numbers and Fibonacci numbers. Now take a closer look at the Lucas numbers. We'll build it up from the middle. Start with 2, then 1 and -1, then 3 and 3, then 4 and -4, and so on. As if the pattern wasn't clear, we look at the Fibonacci sequence too. 0 in the center, then 1 and 1, then 1 and -1, then 2 and 2, and the pattern clearly continues. What's the pattern? If we reverse both sequences and negate every other term, we end on top with the original Lucas sequence, and on bottom with the negative of the Fibonacci sequence. So we codify this as an operation on these sequences. I call it the reverse and flip. We take any such sequence, reverse it, negatize the index, and then negate every other term, we get another Fibonacci-like sequence back. For example, we can check that adding the red plus green terms gives the blue term, or if the first term were one of the negatized ones, it still conspires to satisfy the recurrence. Red plus green still equals blue. Great. So we have this cool operation that acts on sequences, and we know that it leaves the Lucas numbers alone and negates the Fibonacci numbers. But remember, every sequence is built from just these two, so that operating on this random sequence is incredibly easy, and gives us a way to split them up into their Fibonacci part and their Lucas part. In particular, if we add the original sequence with the transformed sequence, the Fibonacci part will cancel, and the Lucas part will double, so you'll get twice the Lucas part of the original sequence. And same with subtracting. The Lucas part will cancel, and the Fibonacci part will amplify, so you'll get twice the Fibonacci part. Now the final step. We take phi as written earlier to be 1 plus square root of 5 over 2, satisfying 1 plus phi equals phi squared. Then we check the sequence 1, phi, phi squared, phi cubed, etc. This is a Fibonacci-like sequence, right? Any two consecutive terms are just a power of phi away from 1 and phi, so adding them gives the same power times phi squared, which is the next term of the sequence. Red plus green equals blue, as before. Now the final question, what is its Lucas part and what is its Fibonacci part? We can figure it out by determining its transformed series. Reversing and flipping, we see that the terms are 1 minus 1 over phi, 1 over phi squared, minus 1 over phi cubed, and so on. Notice that the reversed and flipped is also a geometric sequence, with ratio negative phi inverse. So if we take this reversed and flipped sequence and add and subtract with the original, we get phi to the n plus rho to the n and phi to the n minus rho to the n, where rho is the other root, negative phi inverse. And we know that these are proportional to the Lucas numbers and the Fibonacci numbers. The proportion constant can be checked through one non-zero value, and for Lucas, the constant actually equals 1, and the formula for Ln is written here. We can also check the Fibonacci proportionality constant through f1, because f0 won't work. The sequence gives root 5 when it should originally be 1, So we need to divide by root 5 and get Binet's formula as we originally wrote.
If you know linear algebra, you'll understand that what we did was we wrote down a basis for the two-dimensional vector space of Fibonacci-like sequences, we wrote down a linear operator on that space, and we determined that the basis we wrote down was actually an eigenbasis with eigenvalues 1 and -1. That let us write down a second basis, the geometric sequence basis, and allowed us to easily write down the change of basis matrix and inverse change of basis matrix, which let us write down the original basis in terms of the new one, which is exactly what Binet's formula is. And now we return to the game we started with. Remember, there's 2 piles of stones, and you can take as many as you want from either pile, or you can take the same number from both, and the goal is to take the last stone. We're going to solve this puzzle in 3 steps, representing the 3 levels of insight that we developed.
We'll start by recalling the main conclusion of our excursion into combinatorial game theory. Start at the beginning and alternate between detecting losing and winning positions. Losing positions are those whose only moves are to winning positions, and winning positions are those that have a move to losing positions. Continue this way until we reach the starting state, in which case we're done. Notice here we can list the states as blocks in a 2D grid. The coordinates of the block signify the number of balls in the left and right piles, respectively. For example, the bottom row and left column represent one of the piles being empty, and the origin in the bottom left is the ending position where both piles are empty. What are the moves on this grid? Removing from the left pile is the same as moving to the left. Removing from the right pile is the same as moving down. And removing from both at the same time is the same as moving down left diagonally. So we start by labeling the origin 0, 0 as the losing position, right? It's losing because if you receive this position, you can't win. So we label that red. Now every move that can get to 0, 0 is a winning position. That's everything in its row and column in this main diagonal here. So we color all those green. Now we look at everything that only has moves to green. That's just 1, 2, and 2, 1, right? From 1, 2, going down, left and diagonally, we only ever reach 0, 2, 1, 1, 0, 1, and 1, 0, all of whom are green. But it itself is not yet colored. So it's a losing position, and we color it red. The same exact analysis occurs with 2, 1, so we color it red too. Then again, everything in their rows and columns and diagonals is green. And then where else? Look at 3, 5, and 5, 3. They can't go anywhere except green, so they must be losing positions too. Then everything is green except for 4, 7, and 7, 4, so they're losing. Then continue like this, finding a pair of symmetric losing positions, and then a whole host of winning positions. This is perfectly programmable into a computer, and you could get losing positions as far out as you want. And just knowing these, from any winning position, all you have to do is find one you can move to, guaranteed by their construction, and just repeatedly do so. Here's how it might go playing this game with this answer. Ready to play, babe?
What the fuck?
So that's not very discrete. You gotta pre-compute these positions and keep them on a list. But what if you could compute them on the fly? I mean, looking at the losing positions on the grid, it looks like they're 2 distinct lines above and below the diagonal. There's gotta be a good way to compute these beyond just brute force.
Let's analyze this. First, notice that the entire setup is symmetric across the diagonal. What does it matter if there's 6 stones here and 3 stones here, or 3 and 6? And so notice that every time we determine a new losing position, we get 2 of them, one above the diagonal and one below. Now suppose we're at this point in the process. What can we say about the next losing position below the diagonal? Well, first, it can't be in the currently known about rows or diagonals. And in fact, we claim that the next losing position is the one in the next unused row on the next unused diagonal. Let's state exactly what we claim. Consider the square that is, first, in the lowest row with no losing position yet, and second, in the closest lower diagonal with no losing position yet. We wish to prove that it is a losing position. To do so, there's a few things we need to show. We first claim the following. It is not yet green. This is true because it is not in the same row or diagonal as any other losing position by construction. But what about columns? Can a losing position be in that column? We didn't include it in the definition, but we claim that it is further right than any other red. It is enough to consider only the ones below the diagonal, and a red square above the diagonal has a corresponding red square below the diagonal, which is further to the right. So now consider any currently existing red square under the diagonal, say this one. We make the claim that the column of the square is equal to its row plus its diagonal. For example, this square is in the 5th column, 3rd row, and 2nd diagonal. By way of explanation, we notice that crawling up the diagonal increments the row and column without changing the diagonal, and crawling down the row increments the diagonal and column without changing the row. Now the square we are considering is a higher row than every previous losing position, and it's on a further out diagonal than every previous losing position. So it must be a further right column than every previous losing position too. Great, so we know it isn't yet green. The other piece to it being a losing position is that every square it can reach is green. Considering its column and diagonal, that's easy. Every square in any lower row must be green because they all have a red square in them already. Looking at squares in the same row, it's a little more complicated, but not too bad. Moving leftwards until we hit the main diagonal, the red squares in those diagonals make those squares all green, and then the squares below the diagonal one are either to the right of a red square in their row and are hence green, or are to the left of a red square and must be green for another unrelated reason so that the red square is allowed to be red. And we care about the squares below because symmetry proves that the squares in the rest of the row are green too. Amazing. These are the two things we need to prove that it's a losing position. But there's one final thing we want to know. The diagonal it's on shifts down by 1 every step. This should be obvious. By construction, at each step, the new square is on the next unused diagonal. But a similar argument doesn't work for rows. Even though every new square is on the next unused row, the squares above the main diagonal are in rows too, that we are excluded from using, so the next unused row doesn't always mean the next row above the square we just placed. However, this doesn't apply to diagonals. The squares above the main diagonal don't interfere with the diagonals of the ones below. Anyway, so what have we proven? We've shown that 1, there is a losing position in every row and every column, which means that the row and column coordinates of the non-zero losing positions below the diagonal partition the positive integers. And 2, the losing positions below the main diagonal are in consecutive diagonals, which means that the difference in coordinates equals n. Well, hold on. Look at that. A sequence that partitions n? A wild and crazy guess is that these coordinates are Beatty sequences. Criterion 4 will be the way we distinguish the correct sequence from every other one. Let's pick it apart. If they truly are Beatty sequences, we can plug that in, move one floor to the other side, pull n into the floor since it's an integer, factor it out. Then these two floor sequences are the same, so their coefficients must be equal, since very large n differentiates even very small differences between the two. So that's one equation in alpha and beta. The other is the equation in the theorem we proved. Algebra Autopilot confirms what everything in this video has been leading up to. Alpha is phi, and beta equals alpha plus 1, which equals alpha squared. So our conclusion is that if the losing positions are built of Beatty sequences, they must be those with coefficients phi and phi squared. Of course, the Beatty sequence guess is unsubstantiated, but we can prove there's only one pair of increasing sequences that partition n for which the difference is n. The smaller number in each pair must be the smallest unused number, and the larger number is determined by adding that n. So the sequences must be unique, so the losing positions must be built of these Beatty sequences. So then how does this translate into strategy? Given piles of A and B, we take the difference, and that will be the diagonal you're on, which is your n. Compute floor of phi squared times n and floor of phi times n. This is the pair of coordinates of the losing position on the same diagonal. If the piles are currently larger than these, you can remove enough stones from both to get down to that square. If the piles are less than these numbers, then you remove enough from the larger pile to get into a losing position. And if the piles are equal to these numbers, then you're already in a losing position, and you need for your opponent to make a mistake. It's clearer with pictures. We can divide the set into 3 colors. The purple represents the first case, where we are above the losing position in our diagonal. Then we can slide down the diagonal until we reach it, by removing stones from both piles. the yellow region is made of squares outside of that set. In the half above the diagonal, the losing position in the same column is below it, so you can remove stones from the larger pile to move down to it. And the same for the yellow region below the diagonal. And of course, the red squares are the losing positions, and you need help to win.
Here's how this strategy works in practice.
15 minus 10 equals 5. 5 times phi is 8.09, and times phi squared is 13.09. So I can remove 2 from each and be winning.
What's he doing? What does this game need a calculator for? He must be cheating. That's not fair.
The conclusion of the last section is good enough for basically every other video on YouTube about Wythoff's NIM, because that's where they all stop. But it's not good enough for me. I mean, I don't know how to multiply by 1 plus root 5 over 2 in my head, and I don't expect anyone else to do so either. So we're going to make one more simplification to be able to solve this game in your head a lot easier.
Remember that we figured out how to detect which of the two Beatty sequences a given number lands in. There's a region of width 1 over alpha below each integer. We compute n over alpha, and if it's in that region, it's in the alpha sequence, and if it's not, it's in the beta sequence. So for our purposes, we need to divide by phi. What numbers do we approximately know how to divide by phi? Fibonacci numbers. So the idea is we use the Zeckendorf representation of a given number to approximately divide it by phi, and then be able to move on from there. To do so, we need an exact formula for a Fibonacci number divided by phi, and how close it actually is to the next lower Fibonacci number. This is the point of the video where most algebra happens, so beware. So we use Binet's formula. We take fn minus 1 and subtract fn over phi. Watch the algebra autopilot. We end with rho to the n. Okay, that makes sense. As n gets larger, the fraction gets smaller. But remember, rho is negative. So this difference alternates sign, and so the Fibonacci numbers over phi alternates between being over and under integers. So now we take the Zeckendorf representation of a random integer, divide by phi, and compare to the Zeckendorf representation made up of the Fibonacci numbers of one smaller index. Computing the difference, and using the previous result, we obtain the sum of powers of rho. This difference represents how close a over phi is to b. It should be close, but how close, and is it a positive or negative difference? Since the powers of rho go to 0, we claim that the sign is actually determined by the sign of the smallest power of rho. In other words, that is so large that no matter how many turns of the opposite sign there are, they can't cancel it down. Why is that? Well, say the smallest exponent is n1. We compute z over rho to the n1 and prove that this is positive. The worst this sum could be is adding up every allowed power of rho that is negative, which are cubed, fifth power, and so on. Remembering that we can't use rho to the first because Zeckendorf requires that the included Fibonacci numbers aren't consecutive. But that's a geometric series, and the formula for its sum gives, after some manipulation, negative rho, which we note is positive, which means that z and rho to the n1 have the same sign. So yes, no matter how many other terms there are, this difference will always be the same sign as the smallest term. Now, how large can it get, positive or negative? We again compute z over rho to the n1 and see how positive it can be. As before, the worst case is when all terms are positive, which gives another geometric series. More algebra autopilot collapses it down to negative 1 over rho. We can add back on positivity and replace z with what it was originally defined as, and get a neat pair of inequalities.
Okay, whoa, a ton of math there. What did we actually do?
We took a number a, given its Zeckendorf representation, and came up with another Zeckendorf representation of a number we thought was approximately a over phi. After multiplying by rho to the n1, we learned that if the smallest Fibonacci term's index is even, a over phi is less than b by at most negative rho, which equals 1 over phi. And if the smallest index is odd, multiplying by rho to the n1 switches signs, so a over phi is greater than b by at most rho squared, which equals 1 over phi squared. Notice here that n1 is at least 3, since the first Fibonacci number is 1, which is also the second Fibonacci number. So recall that we never use f1 in the Zeckendorf representation. Well, hold on, check it out. That's exactly the condition for being in the lower Beatty sequence we constructed. Check out the diagram. The green lines have width 1 over phi, and the red lines have width 1 over phi squared, which again add to 1. We plot a over phi and b on the number line, and notice that moving a around, the condition that n1 is even is exactly the condition that a over phi is in the green, which is exactly the condition that a is in the smaller Beatty sequence. So we conclude that a number is in the lower Beatty sequence if and only if its lowest Zeckendorf term has even index. In that case, the diagonal number b is what you get when you decrease each Zeckendorf index by 1. And the corresponding larger Beatty sequence term is a plus b, which, doing the calculation, is exactly the Zeckendorf representation where every index is increased by 1. So as an example, we note that 11 is 8 plus 3, whose smallest index is 4. Decreasing each index by 1 gives 5 plus 2 equals 7, which is the diagonal number, and increasing each index by 1 gives 13 plus 5 equals 18. And therefore, we've shown that 11, 18 is the losing position. In fact, the next one after the 9, 15 losing position we computed.
So how do you actually know if a Fibonacci number is an odd index or an even index? Well, one thing you could do is you could just memorize them. You have 2, 5, 13, 34, 89. These are the odd index ones. They're in the blue. And of course, we forget about 1 because that's F1, and F1 is just the same as F2, so we forget it. And if it's odd, then we decrement. Odd decrement. I came up with that. And if it is one of these red ones, 0, 1, 3, 8, 21, 55, these are the even index Fibonacci terms. And you increment, which again means you take the terms of the Zeckendorf representation and increment each index to get to the other number of stones in the losing position. So again, the one way you could do it is you could just memorize. The second method is to take advantage of these two identities here. f2n plus 1 is equal to fn squared plus fn plus 1 squared, and f2n is equal to fn plus 1 squared minus fn minus 1 squared. So we have examples of those here, but if you take a Fibonacci number and it is the sum of two consecutive Fibonacci squares, it's odd index. If it's the difference of two not consecutive, but with difference 2 Fibonacci squares, then it is of even index. And the third and final way is you have these relations between the Lucan numbers and the Fibonacci numbers. So the Lucan number of odd index squared is equal to 5 times the Fibonacci number squared minus 4. And Lucan number of even index is equal to 5 times the Fibonacci number of even index squared plus 4. And so here it's a minus 4 and here it's a plus 4. So what that says is if it's an odd index, you can square it, multiply by 5, subtract 4, get another square. If it's an even index, you can square it, multiply by 5, add 4. So it sort of determines if it's even or odd. And so these are 3 ways to determine if it's an odd or even on the fly. And I think the easiest one is to just memorize them.
So then what is the actual strategy? So what we do is we compute the Zeckendorf representation for each pile. So this has 11 stones, so its Zeckendorf representation is 8 plus 3. This has 7 stones, so its Zeckendorf representation is 5 plus 2. Now for each of them, if the final term in the Zeckendorf representation has odd index, for example this guy, which is 5 plus 2, 2 is F3, which is odd index, we take each Fibonacci term and we decrement it. So instead of 5 plus 2, it is 3 plus 1, which is 4, and 4 is 7's partner. On the other hand, if the final Zeckendorf term has even index, we increment it. We increment each term. And so for here, we have 8 plus 3. 3 is F4, which is even. So we increment each term, and we get 13 plus 5, which is 18. And 18 is 11's partner. Now, if either stone pile has more stones than the other one's partner, for example, 11 has more stones than 7's partner, which is 4, we can just remove enough stones from the larger one to get down to the smaller one's partner. For example, I can remove 7 stones from here to get to 4. And that is a winning move. So what do we do in the case that each is already less than the other's partner? For example, there's 11 in here, its partner is 18, and there's 8 in here, I added 1, and its partner is therefore 13. 11 is less than 13, and 8 is less than 18. So we can't remove enough from one to get to the other's partner because they each is already less than each other's partner. So the only other move we have available to us is to remove some from both. So how many do we remove? What we need to know is we're on diagonal 3, right? Because 11 minus 8 is 3. So what we're going to do is we take 3 and we write it in a special Zeckendorf form. What's special about it is it has to end in an odd index Fibonacci term. So for example, if it already ends in an odd index Fibonacci term, for example 5, we're going to leave it alone. But if it ends in an even index Fibonacci term, like 3, we're going to allow f sub 1 strictly for just this computation. So we're going to write it as, instead of 3, which is f4, we're going to write it as f3 plus f1, 2 plus 1. Or in the case of 21, we write it as 21 f8 is equal to f7, 13, which is plus f5, which is 5, plus f3, which is 2, plus f1, which is 1. So given an even index term, we can always write it as the sum of all the odd index terms all the way down to f1, which is going to be allowed. So we can always write this special Zeckendorf form for any natural number. What do we do with that? Well, we take the Zeckendorf form and we increment it and we increment it again. And those are the two piles that are going to have to exist. So for example, we have 3 as the difference, as the diagonal, and that is 2 plus 1. We increment them, remembering that 1 is f1, so it becomes 1 and 3, which is 4. Then we increment it again, and we get 2 and 5, which is 7. And these are the two piles we have to end with. So 7 is going to be here, and 4 is going to be here. So we just have to remove 4 from each, and that is a winning move. In the case where each is already equal to the other's partner, then you're already in a losing position, and you can't do anything. So you have to wait for your opponent to make a mistake. And that's the strategy.
Here's how this strategy works in practice.
So there's 10 in this pile. 10 is 8 plus 2. 2 is odd index, so I can decrement and get 5 plus 1. That's 6. So I can remove enough from the 15 to get down to 6. Or 15 is 13 plus 2. 2 is, again, odd index, so I can decrement to get 8 plus 1, which is 9. So I can remove enough from the 10 pile to get to 9. Or 15 minus 10 is 5, so I'm on the 5 diagonal. The special Zeckendorf representation of that is just plain old 5, because 5 is already odd index. So I can increment to get 8, and then increment again to get to 13. So I can remove enough to get to 8 and 13.
He's thinking really hard. Is he thinking about the entire game tree? How many moves ahead can he even think? Did he watch Noah's video on this game? Am I screwed?
So let's recap what we did. We introduced this game, Wythoff's Nim, and asked how to beat it. We introduced 3 mathematical ideas, the ideas of winning and losing positions in combinatorial games, Beatty sequences, and Fibonacci numbers in the Zeckendorf representation. These 3 ideas don't look like they go together, but we wove them together into a tapestry that ended with a strategy for winning Wythoff's Nim every time. Along the way, a few side threads appeared, and I want to see your answers to those problems in the comment section below. Otherwise, subscribe to never miss a video, and I'll see you on the next one.
This is a Noah Doll production.